And we are back to finish off Chapter 9 of Pre-Calculus Made Difficult, in which we will move into the deep end, or relatively deep end, of right triangle trigonometry. In the previous video, I introduced you to the three basic trig functions, sine, cosine, and tangent, and I told you that I would introduce you to the three remaining trig functions in the next video. Well, it is the next video, so let's begin there. The three remaining trig functions are called the reciprocal trig functions because they are defined as the reciprocals of the three trig functions you already know. To be more specific, let's say that for any acute angle theta, we will define this symbol, SEC of theta, which we read as secant of theta, to be the reciprocal of cosine of theta. And of course, we already know how cosine is defined, thanks to SOH CAH TOA. So that tells us, for example, that the secant of 45 degrees is simply 1 over cosine 45 degrees by the definition of secant, which is therefore 1 over, well, you know what cosine of 45 degrees is. It's the same thing as the sine of 45 degrees, namely 1 over root 2. And the reciprocal of 1 over root 2, of course, is the square root of 2. And that's that. Or similarly, the secant of 60 degrees is simply 1 over the cosine of 60 degrees. And again, that is simply by definition of the secant. And then what's cosine of 60 degrees? Well, you remember how that works from last time. The cosine of 60 degrees is the sine of 30 degrees, because the cosine of an angle is the sine of its complement. So this equal sign is justified by a cofunction identity, since cosine and sine are cofunctions, as we discussed last time. And sine of 30 is something that, of course, you memorized last time after understanding why it is so. Sine of 30 is a half, so we get the reciprocal of a half, which is 2. So anyway, there's nothing deep about the definition of secant, literally just the reciprocal of cosine. And now we will define our other two reciprocal trig functions in the same spirit. This funny looking symbol, CSC theta, which we read as cosecant of theta, we define to be the reciprocal of the sine of theta. So for example, the cosecant of 60 degrees is simply 1 over the sine of 60 degrees by the very definition of cosecant, and we can evaluate that exactly because the sine of 60 degrees, as you memorized last time, is root 3 over 2. So taking its reciprocal, we get 2 over root 3, or if you want to rationalize the denominator there, 2 root 3 over 3. And we have it. And even though we have moved on from this point, do not forget why the sine of 60 degrees is root 3 over 2. It all comes from the ratios on a 30, 60, 90 triangle, which is of course half of an equilateral triangle, which means that whatever the short side is, that's half of one of the equilateral triangle sides, which means the hypotenuse is going to be double that. So 2 in this case, meaning that the remaining leg can be found with the Pythagorean theorem, and that's going to be root 3. And then from this picture, we can read off all the ratios, like sine of 60 degrees. There's 60 degrees. We call on SOH CAH TOA. So that's sine of 60 is opposite over hypotenuse, root 3 over 2, and there it is. So be sure you know where this kind of thing comes from, but also know it off the top of your head. Okay, you get the point. And there's one more reciprocal trig function to define, which is expressed COT theta, which is short for cotangent of theta. And I'll bet you can guess how it is defined. It is defined as 1 over the tangent of theta. So that, for example, the cotangent of 30 degrees is 1 over the tangent of 30 degrees, and that's just by definition of cotangent. And hopefully you remember that the tangent of 30 degrees is 1 over root 3, so that the cotangent, its reciprocal, is going to be root 3 itself. And if you have not committed to memory the fact that tangent of 30 degrees is 1 over root 3, which last time I recommended you memorize without quite saying that you really must do it, you could always reconstruct this by drawing that same picture we had a moment ago and reading off the tangent of 30 degrees, which would be up here, as the opposite over the adjacent, which would have been 1 over root 3. But it's nicer just to have it in your head. provided you understand where it comes from. All right, so those are the three reciprocal trig functions. The only thing you have to remember about them, as far as their definitions are concerned, is which one goes with each of the three main trig functions. It's pretty easy to remember that cotangent and tangent go together, but people mix these ones up a lot. I think it's fairly easy to remember them, though, if you just bear in mind that the reciprocal trig functions are strictly heterosexual. S never goes with S, and C never goes with C. So if you're faced with secant with an S, and you can't remember, wait, is that the reciprocal of sine or cosine? Just think, oh yeah, it's got to be cosine. S is going to go with C. Same story over here. Cosecant starts with a C. It's the reciprocal of which function? Oh, it's got to be the one with the S, which is sine. Just a silly way to remember it, but believe me, it will work, and your mind will be free to concentrate on more complicated things. Okay, now the reciprocal trig functions have some interesting, somewhat provocative names. Just like we had sine and cosine in our original trio of trig functions, now we have secant and cosecant. So we might expect a nice relationship amongst them. And similarly, we already met tangent, and here's cotangent. So of our 6 trig functions, sine, cosine, tangent, secant, cosecant, and cotangent, we have 3 cofunction pairs. Sine and cosine, secant and cosecant, tangent and cotangent. And as you might guess, just as we discussed last time that sine and cosine are connected by that nice cofunction identity, the other cofunction pairs are also related by cofunction identities. What we saw last time was that for any acute angle theta, the cosine of theta is the sine of theta's complement. So for example, cosine of 10 degrees is the same thing as sine of 80 degrees, or the cosine of 30 degrees is the same thing as the sine of 60 degrees. And of course you can read it backwards as well. The sine of an angle is the cosine of its complement. So we could write that just as well as the sine of theta is the cosine of theta's complement. Okay, we proved that last time, but the suggestive names of our other cofunction pairs hint at a couple of other important cofunction identities. For example, the cosecant of theta is going to be equal to the secant of theta's complement. Or if you care to turn that around, the secant of an angle is the cosecant of its complement. And finally, what do you expect is true about the cotangent of theta? Yes, you guessed it. It's going to be equal to the tangent of its complement, because tangent and cotangent are, as their names suggest, cofunctions. They make up a cofunction pair. And to complete the symmetry here, we could write that as the tangent of an angle theta, acute angle theta, is the cotangent of theta's complement. I'm going to clear out these rephrasings to give myself a little more room and ask the obvious question. Why are these two supposed identities actually identities? Why do they hold? How do I know that these things are true? We proved this one last time. And you can't just say, well, this is true because they're called secant and cosecant. Well, no, we can call things whatever we want. We have to know that they have the actual properties. It's the properties that come first, and then the names were given. So let's prove at least this one, that secant and cosecant are a honest-to-God cofunction pair. Well, if you remember how we proved the cofunction identity for sine and cosine, it's going to be the exact same kind of argument. We're trying to prove something about any acute angle theta. So let's just imagine that we have a right triangle that contains the acute angle theta. Well, the right angle takes up 90 of the total of 180 degrees. So that means the other two have to add up to 90, which means that the remaining angle must be the complement of theta. In other words, it must be 90 degrees minus theta. So now I have a perfectly general right triangle containing both theta and its complement, which is the kind of thing I'm trying to establish something about in all three of these cases. Let's give the three sides of this right triangle names, such as A, B, and C for the hypotenuse. All right. So if I'm interested in this identity right here, and I want to write down a proof, all I really need to do is show that cosecant of theta and secant of its complement are always going to be the same thing, no matter what theta is. Well, this picture works for any acute angle theta, so let's just compute these things in terms of A, B, and C. So we'll begin over here with cosecant of theta. We know that cosecant of theta is by definition, 1 over sine theta, as we said right here. Wait, how do I remember that? You remember the reciprocal trig functions are straight. You know that this is the reciprocal of either sine or cosine. It's not cosine, because c never goes with c, so it's got to be 1 over sine. All right, so cosecant is 1 over sine by definition of cosecant. You want to keep straight why each equal sign holds. Anyway, sine of theta, in terms of the names of the sides we provided here, sine of theta, SOH CAH TOA. Here's theta, opposite over hypotenuse. So it's going to be b over c. So this will be 1 over b over c. That's just by definition of sine. And of course, the reciprocal of b over c is c over b. Now, we see that cosecant of theta is just c over b. Hypotenuse over opposite, if you want to think about it that way. The only question is secant of the complement the same thing? Well, let's look. The secant of 90 degrees minus theta, what does that mean? That's 1 over the cosine of 90 degrees minus theta by the definition of secant, which is equal to, well, there's actually several ways we could proceed here, but the easiest would just be to look at our picture. Cosine of 90 degrees minus theta, well, there is 90 degrees minus theta, cosine. So CAH TOA, adjacent to hypotenuse. So b over c. So what we have here is 1 over b over c, which is c over b. Same thing we saw for cosecant. So we found that for any theta, cosecant of theta and secant of its complement always turned out to be the exact same expression. Thus, the cosecant of theta is equal to the secant of its complement as claimed. And I will leave it to you to prove that this third identity holds as well, that cotangent of theta is the tangent of theta's complement. The proof, again, is simply a matter of computing what these things are in terms of A, B, and C on our picture. Without writing anything up formally, you can probably see that it works in your head. What's the cotangent of theta? Well, cotangent is the reciprocal of tangent. Tangent is opposite to adjacent. So the reciprocal is going to be adjacent to opposite. So this thing would be A over B. How about this guy? Is it also going to be A over B? Well, tangent of 90 minus theta. Here's 90 minus theta. Tangent, opposite, over adjacent, A over B. Same thing. So even without writing up a proof formally, you can see, if you understand these things, that this does indeed hold for all acute angles theta. Great. You may remember from the previous video, I said something to the effect of trigonometry turns out to be this interconnected web of relationships among the 6 trig ratios, the 6 trig functions. And here you have seen 2 types of relationships revealed already. Of the 6 trig functions, they come in 3 pairs of reciprocal functions, secant and cosine, cosecant and sine, and cotangent and tangent. And of our 6 trig functions, they also come in cofunction pairs, cosine and sine, cosecant and secant, cotangent and tangent. Tangent and cotangent is the very strange pair that works in both of these cases. They are both reciprocal trig functions and cofunctions, making them a very special pair indeed. All right, let's move on to another topic. I'm going to assume you have all this stuff in your notes and probably in your memory already at this point, since it's all quite straightforward. But either way, I am going to erase it to give myself some room as we move into another topic, which I will call right triangle shortcuts. These will just be 2 pictures that will help you speed up your work when you are solving right triangles, at least when you are finding missing side lengths on determined right triangles. You can think of what I'm about to show you as analogous to those Pythagorean shortcuts I showed you back in, I think, the first video, where I said that if we have a right triangle and you know, say, the lengths of the legs, you should not have to introduce a new symbol like c for the hypotenuse and then write, well, c squared is 3 squared plus 5 squared, which is 9 plus 25, which is 34. So c is the square root of 34. There's nothing wrong with that. And that is the right way to do it when you first meet the Pythagorean theorem. But after you've used it a number of times, you want to be able to do it quickly and without having to define new symbols. So our shortcut, which of course we proved, was that all you have to do is write down a square root, and then it's going to be the sum of the squares of these guys. So 25 plus 9 is 34, and that's it. And you just say it by the Pythagorean theorem and you're done. and it makes life much nicer. And we had analogous rules, or rather rule, for the case where you know the hypotenuse and one leg. We don't want to have to write down, well, let's call that a, and then we'll say that a squared plus 6 squared is 8, and we'll solve for 8. No. At this point in life, we can just say it's the square root of the difference of the squares of these things. So that's going to be 64 minus 36, which is 28. And that just follows by the Pythagorean theorem. And we can write that down all at once without going through the algebraic tedium. Anyway, these right triangle shortcuts I'm going to show you let us do something similar when solving a determined right triangle, so that we don't have to stop and implore SOH CAH TOA to tell us what to do and write down new symbols and things like that. It's very good that we did it that way in the beginning, but we're past that now. We never want to forget how to do that, but in practice, we want to move along more quickly, hence the need for some shortcuts. And I'll show you 2 of these. The first applies to the following situation. Suppose we have a right triangle whose hypotenuse we know, I'm going to call it h, and one acute angle of which we know, which I'll call theta. Now, if you were asked to solve such a triangle, what you're being asked to do is basically find the lengths of the 2 legs. Obviously, the remaining angle is the complement of the given angle. That's not hard. And of course, you do know how to find those lengths. Like if we were doing that in the abstract here, what would we do? Like let's say I want this leg adjacent to theta. Let's temporarily give it a name. I will introduce the symbol x. How would we find x? Well, you'd pray to SOH CAH TOA. Oh, great SOH CAH TOA, please once again remind me how to find the leg of this triangle. And SOH CAH TOA would respond, idiot, if I've told you once, I've told you 100 times. Just say my name. Look, you have this acute angle. You want to relate the adjacent side and the hypotenuse. Adjacent, hypotenuse, that's cosine, ka, SOH CAH TOA, you fool. And we would humbly beg his pardon and say, I will waste no more of your time, great SOH CAH TOA. I understand cosine of theta is adjacent over hypotenuse. That's x over h. So if I solve for x, I find that x, the leg I want, is going to be h times the cosine of theta. Right? Right, he says. Now bug off. And we are happy that we have what we wanted, but a little wary about bugging SOH CAH TOA again. So we'll try to find the other leg by ourselves. Let's call that one y. And then, rather than disturbing SOH CAH TOA, we think to ourselves, okay, let's see. I'm given these 2 pieces of information, and I want this guy, y. What relates those 3 things? Well, relative to the angle I know, I've got opposite hypotenuse. Opposite hypotenuse. SOH CAH TOA. Don't wake him up. So is sine of theta. So sine of theta, the opposite y over the hypotenuse h. When we solve for y, find that it is h sine theta. We've done it. Okay, none of that was difficult, but it took up more time than necessary. So I'm going to compress all this information into a shortcut. Given this setup, where I have a right triangle, I know the hypotenuse and an acute angle, rather than introducing new symbols like x and y and praying to SOH CAH TOA out loud or in our heads, let's just recognize that we have already solved this problem once in the abstract. This leg, the leg that is adjacent to the given angle that I was calling x here, that's always going to be h cosine theta, the hypotenuse times the cosine of the angle. So let me just import that onto the triangle itself. And similarly, this leg, which I took the trouble to give a name to, y, and all of that, this leg which is opposite the given angle, that one turned out to be this, the hypotenuse times the sine of the angle, h sine theta. And that's it. That is my right triangle shortcut, the first of 2 that I'll show you. This picture is one everybody should know. No one should leave a trigonometry class without this being firmly in your head. You will use it all the time in calculus, physics, and elsewhere. Let me just show you what I mean. Let's say we have some right triangle, and I know its hypotenuse is 13, and I know one of the acute angles in it is 62 degrees. What are the other 2 sides? I do not want to give them names and then call on SOH CAH TOA and all of that. I just want to be able to write them down at once, just like we did with the Pythagorean theorem. Well, I can do that now because I have this simple shortcut. It applies when I know the hypotenuse and an acute angle. That's what I know right here. It tells me that the side opposite the acute angle is the hypotenuse times the sine of the angle. So this leg in particular, which is opposite 62 degrees, is going to be 13 times sine of 62. It also tells me that the leg that is adjacent to the given angle is the hypotenuse times the cosine of that that angle. So that means this leg right here, adjacent to 62 degrees, is going to be 13 times the cosine of 62. And of course, if I want either of these legs to 2 or 3 or 9 decimal places, I can get them by punching it into a scientific calculator. But I don't need that right now. I just will leave it with the exact value. And that's about all there is to it. Let's do one more, though, just to ram the point home. Here is a right triangle with a known hypotenuse of 42 and an acute angle of 29 degrees. How long are the two legs of this triangle? Well, this triangle matches the situation of our shortcut picture. The side opposite the 29 degree angle, that's going to be the hypotenuse times the sine of that angle. So in this case, 42 times the sine of 29 degrees. This is very easy to remember because we naturally think of opposite as being related to sine, because sine is opposite over hypotenuse. And then the leg adjacent to the angle, well, we naturally think of adjacent as having to do with cosine, because cosine is adjacent to hypotenuse. Anyway, coming back to this one, this is the leg adjacent to the 29 degree angle. So that leg will be 42 times the cosine of 29 degrees. And that's it. We didn't have to introduce new symbols, call one leg A, call the other one B, or call them X and Y, or whatever. We could just write it down all at once and concentrate on other things. And if you need to justify, well, how did you get that? You could just say, by basic right triangle trig. And your teacher will be thrilled, because he or she doesn't want to see all that SOH CAH TOA stuff either, unless you've just been introduced to it that week or something. Or you could even say, by SOH CAH TOA, because, of course, that's where we got these things from in the first place. Or if you like, by SOH CAH TOA shortcut. Whatever. By the time you're out of trigonometry, your future teachers probably aren't going to care. They just will care that you can write these things down and follow them when they are doing it on the board without having to wonder about where it's all coming from. So that's the main one. Everybody should know that. But there's one other one I'll show you that often comes in handy. It's not quite as ubiquitous as this, but it's a nice one to have in your head. It concerns the situation where I have a right triangle, of course I have an acute angle in it, and I have a side, but it's not the hypotenuse. It's the side adjacent to the known angle, so I will call that A. Well, if I have a setup like that, the triangle is clearly determined by angle, side, angle, so I should be able to write down expressions for the other two sides. And I can, and you could do it by calling on SOH CAH TOA and all of that. Give these names, call them B and C or whatever. But if you go through the same kind of argument we did to get our first shortcut expressions, and I highly encourage you to do it, you will find that in this situation, where we know an acute angle and the leg adjacent to it, in that situation, the leg opposite the angle will be a tangent theta. It's that adjacent leg times the tangent. And the hypotenuse, again, by the same type of argument, is going to be a times the secant of the given angle, theta. So I will leave the proof of those two statements to you. It's very easy, and of course it's in the book. But it allows us to simplify our work in situations like the one described here. For example, if we have a right triangle and we know that it contains a 69 degree angle and that the leg adjacent to that 69 degree angle is 4, then I should be able to write down the other two sides at once. Namely, the leg opposite the given angle is going to be 4 tangent of 69 degrees. And again, be clear why this one applies, why I've got a tangent there. It's because I don't know the hypotenuse. The given side was just the leg adjacent to the given angle. So this picture holds. It's the tangent that is involved. And similarly, this side, the hypotenuse, is going to be 4 times the secant of 69 degrees. And like that, we're done. No need to introduce new symbols. No need to call on great SOH CAH TOA. So definitely get this one in your head. Your life will be incomplete without it. This one, I highly encourage you to get in your head. Your life will be simpler with it. But if you don't have it there, it's not the end of the world. Oh, and I should mention, some of you might say, hey, wait a second, you've only got 2 of 3 possible shortcuts. You've got an acute angle in the hypotenuse and an acute angle in the adjacent side. But what if we are given an acute angle like 37 degrees and we know the opposite side? I mean, that's angle, angle, side. It's enough to determine the triangle. Shouldn't there be a shortcut to tell me what those are? There is, but you don't need to memorize anything, because if you know that this angle is 37 degrees or whatever, you know what this angle is too. It's the complement of that. Like in this case, it would be 53 degrees. And now look what you've got. You've got an acute angle and the side adjacent to it. So this second picture holds. It tells you that this side would be 5 tangent of 53, and the hypotenuse would be 5 secant of 53 degrees. So there's actually no need for a third shortcut rule. Okay, as a nice application of these shortcuts, I'm going to show you something that lies in your future. Well, for some of you anyway. Those of you who will be taking the whole calculus sequence will eventually take multivariable calculus. And when you get to multivariable calculus, you'll be dealing with a lot of stuff that takes place in 3 dimensions. So instead of having the familiar xy axes, you'll be looking at x, y, and z axes. The same story holds, though. Given any point in 3-dimensional space, you can get to it by going a certain distance parallel to the x-axis, a certain distance parallel to the y-axis, and a certain distance parallel to the z-axis. And those 3 distances would be your x, y, and z coordinates for that point. So maybe this would be 2, 4, 5, or whatever. But that is not the only coordinate system in town in 3 dimensions. Those are called Cartesian coordinates. But there are other coordinate systems as well, one of which is called the spherical coordinate system. And in the spherical coordinate system, the 3 coordinates for this point aren't given by those 3 linear distances like that. They're given by 3 different values. There's no need for me to go into details because you're not going to be using the spherical coordinate system in this class, but I will point out what they are, and then I will mention what they have to do with these humble right triangle shortcuts. So the way you would identify this point in the spherical coordinate system would be with 3 numbers. The first number would be simply the distance of the point to the origin, and that is called rho. That's another Greek letter for you. Looks like a P, it's not a P, it's a Greek rho. The next coordinate in the spherical coordinate system, the second coordinate, works like this. We drop a perpendicular from the given point down to the plane that contains the x-axis and the y-axis. It's called the xy plane. And we join that point where it lands to the origin. So that gives us a little right triangle right there. This angle here in the xy plane that we have to rotate the positive x-axis to reach that dotted line, that angle is called theta, and that is the second coordinate in the spherical coordinate system. The third coordinate is this angle right here between the positive z-axis and this line that joins our point to the origin, and that is called phi. That's another Greek letter. Anyway, when you're working with these 2 coordinate systems in 3-dimensional space, it's important to be able to convert, to translate from one system to another. So let's say we have this point, and I have given you the spherical coordinates. You know rho, that distance, and you know these 2 angles, theta and phi. And from those 3 pieces of information, you need to find the Cartesian coordinates at that point. In other words, you need to find these 3 lengths, which are x, y, and z, the 3 coordinates of our given point. So my question are, can we find x, y, and z in terms of rho, theta, and phi? And there are some very ugly looking translation equations. And I always tell my students in multivariable calculus, do not memorize those equations. They're horrible, and you'll never remember them. You'll remember them only long enough to take a test, and then you'll forget them, and then it's useless. Instead, just draw this picture, which once you're experienced with these things only takes a few seconds, and use your very basic knowledge of trigonometry, which is the kind of thing you're learning in this class, to get what you want. Namely, you want to be able to write down what is x, what is y, and what is z, where each one of those will be some kind of expression involving rho, phi, and theta, so that we can do our translation. This will be easier if we draw in another dotted line so that it is parallel to this one down here. If we do that, then I have these 2 parallel lines and this green line falling across it. So these 2 angles, those zigzag angles as they call them in the book, are going to be equal. So that means this guy is going to be phi as well. Now I want you to concentrate on this right triangle that I have shaded in. We know an acute angle in it, phi, and we know its hypotenuse, rho. So that means our first shortcut for right triangles applies. That means that the side opposite phi is what? It's going to be rho sine phi, because its hypotenuse is rho, and we're dealing with acute angle phi. Moreover, the side adjacent to phi, that's going to be rho times cosine of phi. But that's z. That's already the first of our 3 conversion equations. So z is going to be rho cosine phi. Terrific, but we still need x and y. Well, that has become easy, because now look at this right triangle that I have shaded. It's in the xy plane. On that triangle, I know an acute angle theta, and I know the hypotenuse, which is rho sine phi. that means I can use, once again, my first right triangle shortcut to get the other sides. In particular, this side, y, which is opposite the given angle, is going to be the hypotenuse times the sine of that acute angle. So y is going to be all that junk, rho sine phi, the hypotenuse, times sine of theta. And that's it. That one's done. As for x, that's going to be the hypotenuse times the cosine of theta, because x is adjacent to theta. So that's the hypotenuse, that yellow stuff, times the cosine of theta. And that's it. Those are our translation equations. And if you understand just this one basic picture, and you understand what is meant by spherical coordinates in the first place, you can recover them in just a few seconds. No one in the world should memorize these things, but they're very easy to recover from a very basic idea that you're learning in the current class. Anyway, that is to come in your future. Point being, it would be very awkward if you found yourself in a multivariable calculus class and you didn't know this kind of thing. So know these right shortcuts well, especially the first one. That is absolutely essential. This one is a nice bonus that you should know, but if you don't know, no one's going to fault you for it. But your calculus and physics teachers will be very upset if you don't know this one. Okay, and now it is time to end this little shortcut interlude and discuss a very fundamental trigonometric identity and its two cousins. So we will finish this up with the so-called Pythagorean trig identities. There are 3 of these, one main one, and 2 minor variations. As you might expect with the name Pythagorean, they all concern squares, in this case squared trigonometric functions, and relationships among the squared trigonometric functions, which reminds me that I need to introduce a little notation that we use for squared trigonometric functions. If we have an expression like the sine of theta, and we square it, the expression starts to look a little messy. And because expressions like this, with powers of trig functions, do arise frequently, we use a simpler notation that's a little easier on the eye. Instead of writing this, we write this. We still read it as the square of sine theta, or sine squared theta. People say it in different ways, but this more compact notation saves us from having a glut of parentheses all over the place. And of course, the same thing holds for all the trig functions. If we write this, well, that simply means the square of cotangent theta. And not surprisingly, we generalize this to other powers of the trig functions as well. So we might write something like this, which simply means the 5th power of cosine theta. And the same idea holds for any of the 6 trig functions and any positive power thereof. I specify positive powers because we have that terrible notation I mentioned in an earlier video for inverse trig functions. For example, if we have inverse sine of a half, we have to remember that is what that means. Inverse sine of a half in the context of solving a triangle means the angle whose sine is a half, which of course we know is 30 degrees. That expression does not mean sine of half raised to the -1 power. Raising this to the -1 power would just mean 1 over sine of a half, cosecant of a half, and nobody cares about that. So this kind of notation is for positive powers. That -1 there is a terrible bit of notation that we're stuck with. And I partially blame calculator companies because there's a perfectly common alternate notation for the inverse trig functions, which is this. Instead of writing inverse sine of a half like that, we write it arc sine of a half. I can explain in the next chapter why arc sine is a somewhat reasonable name for it, but at least there's no confusion. Nobody's going to look at this and say, oh, I think that means 1 over something. No, that's just its own strange thing. You have to know that it means the angle whose sine is a half, so 30 degrees, again, at least in the context of solving triangles, but there's no ambiguity. I said I blame the calculator companies because as far as I can tell, they all put this button on their calculators rather than a button that says arc sine. And if teachers wanted to introduce the inverse trig functions just using arc sine and arc cosine and the rest, they would then have to say, oh, but when you look on your calculator, you're going to see totally different notation. So it's easier just to use the notation that people see on their calculators. But then, I have sympathy with the calculator makers as well, because all those calculators have tiny little buttons, and it's a lot easier to put that symbol on a button than it is to put that symbol on a button. There's just not that much space for it. Well, life is nothing but trade-offs, and this is where we are. The main thing is just to be aware and to get used to it very quickly. But enough of of that. I think you understand this notation. It's pretty straightforward. So I am just going to tell you the main Pythagorean identity, and then I will explain why it is true. For any acute angle theta, the following relationship holds. If we square theta's cosine and square theta's sine and add the two together, we will always get, no matter what theta was, we will always get 1. Strange. So the claim here is that if we took any acute angle whatsoever, 32 degrees, took its cosine, took its sine, squared both of those things, and added them up, we'd get 1. Similarly, if we started with the cosine of 17 degrees and the sine of 17 degrees, and we squared both of them and added them together, we would get 1. And so it would go for any acute angle theta. Why? Why is this so? Well, there are several different ways to see it, and I will show you 2 of them here. First explanation is a familiar sort of argument. Given our angle theta, we construct a right triangle that has theta in it. What are its side lengths? Well, who knows? Who knows what size the triangle is? It doesn't matter. Let's just give them names, our usual A, B, and C. And now let's just compute the stuff on the left-hand side, cosine squared theta plus sine squared theta, in terms of A, B, C. So here's our left-hand side, cosine squared theta plus sine squared theta. What is that in terms of A, B, and C? Well, remember what this notation means. I'm only going to write it out in expanded form probably this one time, and after that you should just know it. That means the square of cosine theta, and the other one means the square of sine theta. Cosine theta, in terms of this picture, CA, adjacent to hypotenuse, that's A over C, so we get A over C squared. Then over here, sine theta, in terms of this picture, SO, opposite to hypotenuse, B over C, so that's plus B over C squared. But basic algebra lets us simplify those terms to A squared over C squared plus B squared over C squared, and now I've got a common denominator, so I can write that stuff as A squared plus B squared over C squared. But hey, wait a second, what do I know about that? A squared plus B squared. A and B represent the legs of a right triangle. So by the Pythagorean theorem, A squared plus B squared is C squared. So I can rewrite all that as C squared over C squared by the Pythagorean theorem, hence the name Pythagorean identity. And of course, divide anything by itself and you get 1, which was exactly as we claimed it would be. This holds for any acute angle theta. Cosine squared plus sine squared is 1. That was the first explanation. I promised you 2. Here comes the second. Okay, so let's suppose theta is some acute angle. I want to prove that this Pythagorean relationship holds. So what'll I do? I am going to build a right triangle containing angle theta, but this time I'm not just going to say, well, what do I care what the side lengths are? I am specifically going to build one in which the hypotenuse is 1. So in this case, I have my unit length hypotenuse. I need a right angle, of course. So I'll drop that, and there's my triangle. Now, I've got a right triangle where the hypotenuse is known and an acute angle is known. So by our right triangle shortcuts, our SOH CAH TOA shortcuts, we should be able to write down what the 2 legs are immediately. This one, that's opposite angle theta, is of course the hypotenuse times the sine of theta. So 1 sine theta, which is just sine theta. And similarly, this leg, the one adjacent to theta, that's the hypotenuse times the cosine of theta. But the hypotenuse is 1, so that is just going to be the cosine of theta. And now, lo and behold, just look at that triangle. What does Pythagoras tell us about that triangle? By the Pythagorean theorem, the sum of the squares of the legs is the square on the hypotenuse. In other words, cosine squared plus sine squared is 1 squared, which is 1. And that's exactly what we were trying to prove. Ta-da! You can't get much more simple than that. And again, of course, this holds for any acute angle theta. There was nothing special about the fact that this looks like this one might be, 70 degrees or whatever. Put it in a different position. If that's 1, this guy is still sine theta, and this guy is still cosine theta. And by the Pythagorean theorem, cosine squared plus sine squared is 1. And that, I think, gives you a very direct insight as to why this thing is called the Pythagorean identity. And notice how nice it was to use our right triangle shortcuts there, rather than introducing new symbols and saying, well, let's call this one y, and then we know that sine of theta is y over 1. We just saw it all at once. Good. So by now you should thoroughly understand why this Pythagorean identity holds. This will be used frequently. You'll see it a lot in calculus, for example, where after some algebraic manipulation in some expression, you'll end up with things that look like this on the inside, and they will collapse nicely into ones, which will make your life easier. This identity will be your friend. And notice that it gives us another relationship between sine and cosine. We know that those two functions are related by the cofunction identity for sine and cosine, but here they are related by a Pythagorean identity as well. And I mentioned that there are 3 Pythagorean identities, each of which connects a pair of the 6 trig functions. So let's move on to the other 2. This one is by far the most commonly used, but the other ones come up now and again as well, especially the one I will show you next. And rather than writing it down all at once and then explaining why it's true, like we did with this one, I'm going to show you that you can derive the second one from the first one in a matter of seconds. And this is something you will end up doing in the future on your own, because you'll forget the exact form of this second one. But if you know the main one, you can derive it in seconds. All you have to do is divide both sides of this equation by cosine squared theta. Let's think about what happens if I do that. If I divide the left side of this equation by cosine squared theta, that means I divide each term by cosine squared theta. What happens when I divide the first term by cosine squared theta? Well, I get cosine squared theta divided by cosine squared theta. That's obviously 1. Okay, now I divide sine squared theta by cosine squared theta. What does that give me? Hopefully you see it all at once, but just in case, I'll scratch it out down here. We get sine squared theta over cosine squared theta, which, as your algebraic reflexes tell you, is the square of the quantity sine over cosine. But what is sine over cosine? That's an identity you learned last time. Sine over cosine is tangent theta, and we're squaring that, so we would write that in the usual notation we use for powers of trig functions. So going back to our picture over here, if I divide both sides by cosine squared theta, that's going to give me 1 plus sine squared over cosine squared, which is going to be tangent squared theta. Good, but of course, if I divide the left side by cosine squared theta, I have to divide the right side by cosine squared theta. And what's a short way of writing 1 over cosine squared theta? Hopefully you see it at once, but if you don't, then at least this one time I'll write it out in detail down here. So you should be able to do this in your head. 1 over cosine squared theta. Well, again, just your basic instincts from knowing the algebra of exponents tells you that's the square of 1 over cosine theta, right? Because you square the top and bottom, 1 squared is 1, the bottom squared is, well, cosine squared theta. And what's 1 over cosine theta? Well, we talked about that at the very beginning of this video. The reciprocal of cosine is, of course, one of our reciprocal trig functions. It's going to be secant theta, and we're squaring it, but by now we know we don't write it that way. We write it like this. So going back to our picture here, we're dividing both sides by cosine squared theta. On the left, we get 1 plus tangent squared theta. On the right, we get secant squared theta. And that's it. That is our alternative Pythagorean identity. We don't use it as often as this one, but it definitely has its uses, as you will see in calculus. And notice that it is similar in spirit. It connects the squares of 2 trig functions and a 1. And in this case, it ties together the tangent and the secant, or rather their squares. Those are not cofunctions, like the 2 functions were in our main Pythagorean identity, and they're not reciprocal functions or anything like that. This is just an entirely new relationship. This first one clearly should be memorized. This second one, this is one of those ones where I'd say, it's good to know it off the top of your head, but do you have to commit it to memory? Maybe not. As long as you remember the basic shape of the equation. As long as you remember that there is a relationship connecting tangent squared, secant squared, and 1. You might not remember how it fits together. Is it 1 plus tangent squared is secant squared, or 1 plus secant squared is tangent squared, or tangent squared minus 1? What is it? That's okay if you can't quite remember that, as long as you know the shape, as long as you know what the ingredients are, because it literally takes seconds to rederive it from the main Pythagorean identity. Just remember how you do it. You divide both sides by cosine squared, and you get this alternate version. If you remember that, then it's perfectly fine just to remember the basic shape, the ingredients involved, without nailing it down in every detail in your memory. All right, and the third and final Pythagorean identity, I'll bet you can guess what it's going to look like. It's going to involve a 1 and the squares of 2 other trig functions. Which ones? Well, the 2 trig functions that aren't there already. What's left? cotangent and cosecant. What's it going to look like precisely? Well, I can derive it just as simply as we derive the second one. We're going to start with the main Pythagorean identity and divide both sides by sine squared theta. And let's just see if we can do this in our heads. Well, I'll end up writing some things in the basement, just so everybody's on the same page this first time. But eventually, rather quickly, I hope, you'll be able to do it completely in your head. So let's divide the left-hand side of the main Pythagorean identity by sine squared theta. What am I going to get? Let's start with the easy part. I've got to divide sine squared theta by sine squared theta, so I'm certainly going to get a 1. Okay, but to that I need to add what I get if I divide cosine squared by sine squared. Let's think that one through down here carefully. What's cosine squared over sine squared? Well, of course, by the basic algebra of exponents, that is the square of the expression cosine over sine. And you might think, cosine over sine, cosine over sine. Oh, damn, I wish it was sine over cosine, because I know sine over cosine is tangent. This is the reciprocal of that. Well, use that fact, right? You just told me the stuff we have in there is the reciprocal of the thing we want, sine over cosine, or at least the thing with which we're familiar. And sine over cosine, we like that because we know that is tangent. So we've got all that stuff, 1 over tangent squared. But hey, 1 over tangent, what's that? That's cotangent. And we're squaring it, so we get the square of cotangent. So go back to what we were doing. We were dividing both sides by sine squared. We divide the left-hand side of the main Pythagorean identity by sine squared. Clearly we pick up a 1, but we're also going to pick up a cotangent squared. And again, doing that in our heads, we would probably just think, all right, I get cosine squared over sine squared. Oh, so that's cotangent, square it, and I get cotangent squared. Anyway, we still need to divide the right-hand side by sine squared. Do you see what that's going to be? 1 over sine squared. That's the square of 1 over sine. And 1 over sine is, of course, cosecant. So we get the square of cosecant. And now we have our third and final Pythagorean identity. 1 plus cotangent squared is cosecant squared. And again, no need to memorize this one. Just know it exists. Know the basic shape. Recognize that it looks almost exactly like this one. It's just that the tangent and secant have been replaced by their cofunctions. This main one gets used all the time. The second one gets used with some frequency. The third one every now and again. So be sure that the first one is firmly committed to memory and you have a good acquaintanceship with the second one. You know its shape and at least a passing acquaintanceship with third one. I can tell you that if I ever needed to use this third one, I would definitely need to pause and derive it from the main one because I might be afraid that I'd forgotten exactly what the identity was, which is fine. It takes seconds. Now, there's a very good question you might ask about these two alternate Pythagorean identities. We saw two different explanations as to where the first one came from, and we got the second and third just as easy corollaries, just a simple algebraic manipulation. But we might ask, hey, our explanations of the first one were geometric in nature, and that was pretty satisfying. Whereas these, sure, they were easy, but it's nice to be able to see why these are true in the same way that we could see that the first one was true. Is that possible? It is possible. I explained this one in two ways, and the first explanation, where we just drew a general right triangle containing angle theta, and we labeled the sides A, B, and C, and then computed the left-hand side and saw that it was 1, that style of explanation could be used for these other two as well. And I encourage you to do that, maybe with this second one, just to see how it shakes out. Compute the left-hand side, compute the right-hand side, and you'll see that you get the same thing. You'll have to do a little algebra. At some point, you will use the Pythagorean theorem, but it's all pretty straightforward. But what I want to show you is something more akin to our second explanation of why this first one held. And I can build up an interesting picture that actually includes explanations for all three of these things simultaneously. So let me start by reconstructing the picture we used in our second proof of the main Pythagorean identity. For that one, we started by building a right triangle that contained the acute angle theta and whose hypotenuse was 1. And when we did that, our little SOH CAH TOA shortcuts immediately gave us the lengths of the legs, which were sine of theta and cosine of theta. And then Pythagoras can just look at that right triangle and say, well, of course, cosine squared plus sine squared is 1, and we are done. Well, what I want to do now is extend this same picture. I want to take this lower leg, where I have my cosine theta, and just continue it on outwards, and then come up here to this top vertex of my triangle. I want to draw a line that's coming out of it and is perpendicular to the hypotenuse of my original triangle. So something like this. And now I actually have three right triangles. I have my original one, I have this one over here, and then I have this large one that encompasses both of them. Well, let's think about these triangles for a little while. In my original original triangle, we had a right angle, and then we had this acute angle theta. So the other acute angle, which I'll just indicate by an orange star, is of course the complement of theta. Now it turns out, and we saw something like this in a previous video, that the three triangles I mentioned are all similar. After all, let's think about the big triangle. It's a right triangle, and it contains angle theta. So its remaining angle has to be the complement of theta, which we've already said is the orange star. So our original triangle and the big triangle are clearly similar to one another by angle, angle, or angle, angle, angle. They have all the same angles. They both have a right angle, they both have literally the same angle theta, and they both have the orange star, the complement of theta. And then if we look at this other interior triangle on the right, it's a right triangle that contains theta's complement, the orange star, which means that its remaining acute angle is the complement of orange star, which of course we know is theta. So it too has all the same angles as both our original triangle and the large triangle. So all three of these right triangles are similar. And I want to put that similarity to use to figure out the side lengths in the big triangle. I'll do that by setting up a proportion, comparing that big triangle to the original small triangle on the left, whose side lengths we know already. This is one of those cases where I think it will come out a little cleaner if we name some of the points that we'll be referring to. So I'll call this one O, I'll call this one point P, I'll call this one point Q, and I will call this one R. Okay, so I said I want the lengths of the big triangle, which now I could just call triangle OPQ. We know side OP is 1. Let's see if we can figure out PQ. Well, what do we know about PQ? Let's consider the ratio of PQ to PO. So that's PQ to 1. I'm interested in a ratio of sides because I know that that ratio will be equal, by similar triangles, to the corresponding ratio on our original triangle, triangle OPR. Well, what is the corresponding ratio over there? Well, let's think about what PQ to 1 represents on the big triangle. PQ is the side opposite theta, and 1 is the side adjacent to theta. So I want that same ratio on my original triangle, where the side opposite theta is sine, and the leg adjacent to theta is cosine. So this is going to be equal to sine theta over cosine theta. But we know what that is. We've used it several times already. Sine theta over cosine theta, by an identity we discussed last time, is tangent theta. So I will just say by a basic trig identity. Doesn't really have a name, that one. So what have we just demonstrated? PQ over 1, which is of course the same thing as PQ, is equal to tangent theta. Aha! So side PQ is tangent theta. Excellent. What about side OQ, the hypotenuse of the big triangle? Well, we could proceed the same way. We know that OQ, we could say, is OQ over 1, which is worth looking at because that is a ratio on that big triangle. It's the hypotenuse to the leg adjacent to theta. And that ratio is going to be equal to the corresponding ratio on our original triangle, to which the big one is similar. Hypotenuse to leg adjacent to theta on the original is 1 to cosine. So I'll write that down. Good. And again, that equal sign is justified by similar triangles. But 1 over cosine theta, what's that? Well, go back to the first minutes of this video. The reciprocal of cosine is secant. Aha! So OQ, the hypotenuse of our big triangle, is secant theta. So I will go ahead and write that on here. So now we know all three sides of our large right triangle. Let's call Pythagoras back into the room and ask him what he sees. Well, of course, by the Pythagorean theorem, we have 1 squared, or 1, plus tangent squared is secant squared, which is exactly our alternate Pythagorean identity. So we can see it, and in this very interesting manner where we see both identities portrayed simultaneously. And some of you are probably thinking, and this is a good thought, oh, let's look at this other triangle now. I bet that's going to give rise to the third identity. It's an excellent instinct, but it's not quite right. You can figure out what side RQ is, but what the Pythagorean theorem would tell us in that case is not terribly interesting. You can figure that out on your own if you want to. But it is in fact possible to see this third version of the Pythagorean identity if we extend this picture a little bit more. So just for fun, let's do that. What I want to do is take this side PQ and extend it. And now from vertex O, I'm going to draw a line perpendicular to OQ. And now I have this new point where they intersect. Let's call call it S, and a new triangle, OSP, which of course is a right triangle. And I claim that this one too is similar to all the ones we've been working with. How do I know that? Well, let's start down here at angle POS. POS. How big is that angle? Well, we have a right angle here, and part of it is taken up by theta. So the rest of it has to be the complement of theta, since the two add up to 90 degrees. Well, what's the complement of theta? In our picture, that's the orange star. So there it is, our orange star. And now the rest is clear. In my new right triangle, I have a right angle and an orange star. So the remaining acute angle is the complement of the orange star, which of course we know is theta. So there they are, the same old three angles. So yes, this new triangle is similar to all the other ones we've been working with. And I claim that if we can find the lengths of SP and SO, the Pythagorean theorem on that new right triangle will deliver our third Pythagorean identity. Let's justify that claim. What's SP? Well, whatever SP is, it's a leg of a right triangle whose other leg is 1, so let's consider that ratio SP to 1. What does that correspond to geometrically? SP is the side adjacent to theta, 1 is the leg opposite theta. So that ratio is going to be equal to the corresponding ratio on any of these other right triangles. Let's go back to our original triangle and compare it there, since we know everything about that original one. There, the leg adjacent theta is cosine theta, and the leg opposite theta is sine theta. So we're going to get cosine theta to sine theta. Well, what's that? Hopefully you see it already. But if you don't, let's just think it through. The reciprocal of this thing, sine to cosine, we know is tangent. But it's upside down here. So what happens if you turn a tangent upside down? In other words, if you take 1 over tangent, the reciprocal of tangent, of course you get cotangent of theta. And that's that. SP is cotangent of theta. So let me go ahead and write that one down. All right, what about SO? Well, let's do the same thing. So, SO is the hypotenuse of a right triangle that also contains a side of length 1. So let's consider SO as being SO over 1, that particular ratio, which is the hypotenuse to the side opposite theta. That's going to be equal to the corresponding ratio in our original right triangle, to which this one is similar, where hypotenuse to side opposite theta is 1 over sine theta. But what is the reciprocal of sine theta? That is cosecant of theta. So is cosecant theta. So let's write that down in the appropriate place. Mr. Pythagoras, please return and tell us what you see on this new right triangle. I see, says Pythagoras, that 1 squared, in other words 1, plus cotangent squared, must be cosecant squared for any theta whatsoever. And that, of course, is our third and final Pythagorean identity. So all three of them are visible in this single picture, which is pretty neat. In Chapter 10, we'll see something similar, which will also explain why tangent is called tangent and why secant is called secant. So stay tuned for that. We have covered a lot of ground in this one, so I'm going to end this video here. See you next time in Chapter 10, when our triangles will start to morph into circles. Goodbye.